Hello, and welcome to a digital differential equations lecture video for Salt Lake Community College. In this video, we are going to be continuing chapter 2.4, mixing problems. Consider a tank that is filled with water, and then some substance, call it X, maybe this is a pollution or a salt, but some substance X is flowing into it at a constant rate. The contents of the tank are mixed uniformly and then flows out at the same rate as the inflow rate. Since the inflow and outflow rates are the same, the volume of the tank stays constant. We seek to describe the amount of the substance in the tank at any time. To do this, let's let x of t be the amount of the substance in the tank at any time. We do not know what x of t is. However, our goal is to find x of t. Then x prime of t is the rate of change of this amount, which we can describe as the difference between the rate at which the substance flows into the tank, which we call rate in, and the rate at which the substance flows out of the tank, which we'll call rate out. As an equation, this looks like dx dt is equal to rate in minus rate out, where our rate in is the concentration of the material coming in times the flow rate in, and rate out is concentration out times flow rate out. Let's look at some examples so we can get some familiarity with how this works. Consider a tank that initially contains 50 gallons of pure water. A solution containing 2 pounds per gallon of salt is pumped in to the tank at a rate of 3 gallons per minute. The mixture is stirred constantly and flows out at the same rate of 3 gallons per minute. Our question is, how much salt will there be in 20 minutes? To help you visualize this, I like to draw a picture of the tank. So maybe over on the side, let's make a little image. And let's draw your best three-dimensional tank. So we'll draw the top, the sides, the bottom. We'll have some spout to drop the water into the tank, and then there'll be some spout for the water to exit the tank. Now, to piece all this information together that's given to us, we're told that the tank initially gains 50 gallons of pure water. So here's your 50 gallons of pure water. We know a solution is flowing into the tank at a rate of 3 gallons per minute. But it's not just pure water coming in. There's some salt mixed in here. Now, initially, there's no salt in the tank. It was pure water. But as the water flows into it, there is some salt particles that start to accumulate. Now, the tank stayed stirred, so after a while, the water that's flowing out of the tank isn't going to be pure water. It will at the start, but after a while, it'll start containing some salt as well. And our goal now is to be able to describe how much salt is actually in the tank. How much salt is here in the tank after 20 minutes. To start with, let's let x of t be the amount of salt in pounds. It's measured in pounds. At any time t. Remember, we do not know what x of t, but our goal is to find x of t. Now from this, we'll write a differential equation. If x of t is the amount of salt in the tank at any time, then what is dx dt? Let us first consider the units. Now, the units are incredibly important. If you keep track of the units, it'll help make sure that you get the right answer. So remember, if x is measured in pounds, and in this problem we're measuring time in minutes, then dx dt is going to be measured as pounds per minute. So remember now, dx dt is supposed to be the difference of the flow rates. It's supposed to be rate in minus rate out. Where individually, these flow rates are a product of two other terms. So if we look back at your notes, remember your flow rates. Your rate in is going to be your concentration in times your flow rate in. Your concentration times your flow rate. So we were told that it's coming in at 2 pounds per gallon. This is your concentration. It's how much pounds of salt per gallon that's coming in. So we'll put the 2 pounds per gallon. Again, it's incredibly important that you keep track of your units here. And then times your flow rate, and that's this portion here, the 3 gallons per minute. Now, if you're keeping track of your units like I'm suggesting, then you'll notice that the units of gallons on the denominator here will cancel with the units of gallons here, leaving an answer that can be measured in pounds per minute, which matches the units that we have on the left side of our DE. So pounds per minute, it will equal something that's measured in pounds per minute. Now for the rate out, our concentration term. We don't know the concentration term right away. Remember, your concentration is a measurement of pounds per gallon. But we don't know how many pounds is in there at any given time. Remember, initially, there isn't very much salt in here. But as time goes on, more and more salt is in the tank. And that's what we want. So remember, we said that X of T is going to be the amount of salt in the tank. So it'll be X measured in pounds, now divided by the volume, which there's 50 gallons to start. And since the flow rates are the same, there's always going to be 50 gallons in the tank. I think I'm writing this kind of small. Let me see if I can get this a little bigger, actually. So it'll be X of T, which is measured in pounds, divided by your constant 50 gallons, times our flow rate out, which we were told it leaves at the same as the inflow rate, of 3 gallons per minute. So again, if we're keeping track of units, then this 50 gallons, the units of gallons cancels with gallons here, and we're left with something measured in pounds per minute, which again match the left side of our differential equation. Once we know all our units match, I'm going to stop writing the units to simplify our expression. And so maybe we can write this now as x prime, so dx dt, is equal to, and now our first term here is going to be 6 minus, and our second term, I think we're going to have x of t, 3 and 50. I'm going to rewrite this as 350 is x. And I'm not going to write x of t. I'm leaving it to be implied that x is a function of time. I also include my initial value. We know initially there was pure water in the tank, so that x of 0, x of 0 is 0. Remember, x is the amount of salt in the tank, and initially it's pure water, so the amount of salt at time 0 is 0. This is our initial value problem. Now, how you solve this initial value problem is up to you. We've covered several methods for solving first-order linear differential equations. If you didn't recognize this was linear, maybe it would help to probably rewrite this as x prime plus 350 is x equals 6. So it matches the form of a first-order linear differential equation. So again, you have several methods up to you. You can use the integrating factor method to solve this. You can use the non-homogeneous principle. And so maybe in our videos, my examples, I'm going to do some each way so you can get a familiarity for the method that you might like best. However, for this example, I'm going to use the integrating factor method. So let's go look at the integrating factor. Remember, our integrating factor mu is equal to e to the integral of p of t. In this example, the p of t, you remember, is always the coefficient in front of x. It's the 3/50ths. So 3/50ths dt. Remember, the integral of 3/50ths dt is going to be 3/50ths t. Now remember, our method for the integrating factor method now says multiply everything by the integrating factor. So we're going to have x prime times e to the 3/50ths plus 3/50ths x e to the 3/50ths t equals 6 e to the 3/50ths t. Remember, the integrating factor should have the property that it allows us to rewrite the left-hand side as an application of the product rule. And the easiest way to write it as a product rule is to remember the form. It's always going to be x integrating factor. But as soon as you write this, you should double check and make sure that this does satisfy the product rule. So if you're going to check this product, the derivative of this product, you should have the derivative of the first, x prime, times the second regular, plus by the product rule, the derivative of the second. So the derivative of e to the 3/50ths t is e to the 3/50ths t, times by the chain rule, the derivative of this 3/50ths t, which is this 3/50ths, times x, your first. So this does satisfy the product rule. We have the correct integrating factor. We now choose to integrate each side with respect to t. Oh, I said t, but I wrote u. With the expectation that the left side, the integral of the derivative, will cancel. We have x e to the 3/50ths t plus some arbitrary constant of integration. The right-hand side. Now, technically, the right-hand side is a u substitution problem because it's not just e to the t, it's e to the 3/50ths t. But generally, integrating exponential functions is very straightforward because we know the derivative of an exponential is an exponential, which allows me to say that the antiderivative is probably e to the 3/50ths t. However, I know it's not exactly that because if I were to take the derivative of e to the 3/50ths t, it would be e to the 3/50ths t times by the chain rule, the derivative of this 3/50ths, which I do not have in my original integram, which tells us that we should probably divide by this 3/50ths. Plus some arbitrary constant of integration. Now, we've had a lot of discussion about these constants. Technically, they're different. And I'm going to be combining them, and I'm not going to keep track of my manipulation of the individual constants. So in this next step, let's simplify some of this. On the left-hand side, we'll subtract the C1 so that the C1 and the C2 are combined together. I'm subtracting those. And so we'll have x e to the 3/50ths t equals, now here you probably want to do this division, 6 divided by 3/50ths is going to be 100. You might want to confirm that on your calculator. E to the 3/50th t plus some constant, where this c is really the difference of C2 and C1. And now to solve for x of t, we'll divide everything by e to the 3/50th t. I wrote that kind of small as I was running out of room. And we get x as a function of t is going to be 100 plus c. And rather than dividing by this e to the 3/50th t, I'm going to introduce a negative exponent and write an e to the negative 3/50th t. This is our general solution. We should still solve for our constant though, so we know that x at time 0 should be 100 plus c e to the 0, and we knew initially there was no salt in the tank, so this would have to be 0, so that we have 100 plus c equals 0. C has to be negative 100. So then our model is going to look like x of t is going to be 100 minus 100 e to the negative 3/50th t. Now, our question was asking us, how much salt will there be after 20 minutes? Now, graphically, we should be looking at this problem like this. Let's make a little sketch, a very rough sketch of what this looks like. And here's time. And here's the x of t, the salt in the tank at any time. We knew that initially there was no salt in the tank. Started at 0. However, as time went on, salt started to accumulate. So the way you should imagine this is now salt is starting to grow over time. And so we're trying to say after 20 minutes, how much salt is in the tank at any time? So let's find x of 20 by plugging 20 into our equation for t. I hope you're double checking this on your calculator for me. I hope what you're coming up with is approximately 69.9 pounds of salt will be in the tank. So up here it'll be about 69.9 pounds. Now, this particular question does not ask what the limiting amount of salt is, but I think it's something that we should talk about for a moment. So I'm going to look back at our model, our initial value problem, and ask a question that we did not ask earlier. is there an equilibrium solution to this differential equation? So remember, an equilibrium solution occurs when x prime is equal to 0. Well, for x prime to equal 0, we would require 6 minus 3/50th x to equal 0. And we can solve this for x. Maybe I'll move the 3/50th to the other side of the equation. And now divide both sides by 3/50ths to get x is equal to 100. So we find that there is one equilibrium solution. It happens when there's 100 pounds of salt in the tank. So that tells us that if there's 100 pounds of salt in the tank, then even though there's salt coming in, it's not increasing its concentration. It's the same as what's already there. Graphically, this tells us that the equilibrium solution at 100, which would be here, should be the value that this salt content is approaching over time. And this should make sense if we imagine our solution. And let's look at this last term here. As time goes on, what happens to e to the negative 3/50th t? The e to the negative 3/50th t. As time goes on, this term, because it's a decreasing exponential function, this goes to 0. Of course, 0 times 100 is 0, so it's going to be 100 minus 0. As time goes on, this is going to be asymptotically approaching this equilibrium solution. Okay, this completes everything that we needed to know for this example. And I want to do at least one more of these with you. So let's go to the next page. A tank initially contains 1,000 liters of brine. And just so you know, brine is a technical term that means salt water. Brine is salt water. And in it there is 15 kilograms of dissolved salt. Pure water enters the tank at 10 liters per minute. The solution is kept thoroughly mixed and drains out at the same rate. Our question is, how much salt is present at any time t? When will it reduce to 2 kilograms? Remember, it started at 15. Pure water is entering the tank. So if pure water is entering the tank, it's going to dilute the mixture. And eventually it'll reduce it to 2 kilograms. We want to know when. So let's start by defining our variables. Let's let x of t be the amount of salt measured in kilograms at any time t. Now remember, we do not know what x of t is, but we will find x of t. Now what I would like you to do is write me a differential equation, or write me an initial value problem. And I'd like you to pause the video while you do this. Just take enough time to write the initial value problem, and then let's come back and make sure we have the right differential equation. I'll see you in a moment. Okay, I hope you paused the video. Let's see how you did. our differential equation, we're going to write it as dx dt. And remember, I think the units are incredibly important. So if we were to identify the units right here, the units, so if x is measured in kilograms, dx dt would have to be kilograms per, and this problem is measuring in time in minutes, so kilograms per minute. Remember, your differential equation is always going to be the difference of your rates, with the rate in minus the rate out, where each of these, again, individually is the product of two terms. So let's look at the rate in. We're told that pure water enters the tank. If pure water is entering the tank, then the amount of salt entering is going to be measured as 0 kilograms per minute. Because it's pure water, there's no salt coming in. And it's coming in at a rate of 10 liters per minute. And I noticed I had a unit issue. I said 0 kilograms per minute. That's not a concentration. I should have said it's 0 kilograms per liter. Zero kilograms per liter. That's a concentration. And if we're keeping track of these units, notice that the terms of liters and liters, the units will cancel, leaving something measured as kilograms per minute, which matches the units on the left-hand side of our DE. Now, it is going to be 0 kilograms per minute, but I want to make sure the units matched. Now the rate out term. So remember, this concentration has to be the quotient of how much is there at any time divided by the volume. We don't know how much is there at any time, but we did say it's going to be x of t. And so x of t is going to be your quantity of salt. So x of t kilograms. And we also said that the inflow and the outflow is the same. That means that the volume is going to stay constant at 1,000 liters. And the outflow rate was 10 liters per minute. Again, if you're keeping track of units, the units of liters and liters will cancel, and we'll be left with units of kilograms per minute like we wanted. Once I know that the units work out, I stop writing the units. And so your initial value problem that I wanted you to come up with is going to be x prime is equal to, now remember, this first one is 0, which means this entire rate in is 0. So it's just going to be negative. And here you have the 10 divided by 1,000. I'm going to write that as a decimal, 0.01x. Let's include our initial conditions. We're told initially that was 15 kilograms of salt. So it tells us x at time 0 is 15 kilograms. This is our initial value problem. Now you will notice this is still a first order linear differential equation. However, there's no constant term like on the previous example. And so we get to pick which method that we want to use to solve this. When I look at this, I won't always pick the easiest method. And what I'm noticing is the form of this differential equation. X prime is negative 0.01x. This is a homogeneous first order differential equation that could be solved using separation of variables. Now, you don't have to do the separation of variables by hand. However, for this video, I am going to do it by hand just to remind us of the process. So remember, for separation of variables, rewrite the left-hand side as dx dt. And then for separation of variables, we only get all of the variable x on one side of the equation and all the t's on another. So I'm going to divide, but I'm going to divide just by x. I'm not going to divide by the 0.01. So I'm going to write this as dx over x equals negative 0.01 t dt. Now that we've separated our variables, we'll choose to integrate each side with respect to the variable present, which will give us the natural log of the absolute value of x plus some constant. Right-hand side, the antiderivative of negative 0.01 dt is negative 0.01 t plus c. Again, technically, these constants are different, but I'm going to be combining them in just a moment, and so I don't see a huge need to differentiate between the two. So now let's solve this equation for x. We could probably argue that we don't need the absolute values, because remember, x is measuring the amount of salt at any time. We're never going to have a negative amount of salt, so we could probably drop the absolute values here. Subtracting the c1 from both sides, we can simplify this equation and write it as just the natural log of x Oh, and I didn't write the natural log part of natural log, the n. So natural log of x equals negative 0.01 t plus c. We can choose to exponentiate each side of our equation with respect to e, with a base e, with the expectation that the left-hand side will now just become x. Remember, with the right-hand side, don't write two different exponentials here. It's not a sum, but you could write it as e to the negative 0.01 t times e to the c. And remember, if c is some constant, e to the c is still some constant. So I can write this now as x of t is c e to the negative 0.01 t. This would be our general solution. However, we had an initial value problem. We knew that at time 0, this is 15. So solving for the initial value problem, we know x of 0 is going to be c e to the 0. And this had to be 15. So c is equal to 15. So our model is going to be x of t equals 15 e to the negative 0.01 t. This is our model for solving about the amount of salt in the tank at any given time. Now, graphically, and well, the problem at hand was we were asking how much time to reduce to 2 kilograms. And I first want to think about this problem graphically. So let's make a little sketch on the side here. We have time, the amount of salt, and remember, we started this problem, this initial value problem, with 15 kilograms of salt in it. Now, if we look back, recall, we said that since fresh water is flowing in, it's going to be diluting the amount of salt in the tank. And so it's going to be reducing over time. And our solution tells us that, is that at time 0, this is 15. But as time goes on, this e to the negative 0.01 term gets smaller and smaller and smaller because it's a decaying exponential function. So we can anticipate that as time goes on, we're going to be reducing the amount of salt content, and it'll look something like this. Now, our differential equation should also confirm this, but we should look at this and recognize that there is one equilibrium solution. The only time that x prime is 0 is if x is 0. So we should be anticipating we have one equilibrium solution that's down here at x equals 0. So our question is, when will it reduce to 2 kilograms? How much time to reduce to 2 kilograms? We're asking when is 15 e to the negative 0.01 t, when is this eventually equal to 2 kilograms? So if we're going to solve this now for t, let's divide both sides by 15. So this would be e to the negative 0.01 t. I'm going to leave this as a fraction, 2/15. We can choose to take a natural log of both sides so that the natural log and the e, the exponential function, will cancel to get negative 0.01 t is the natural log of 2/15. Or finally, t is the natural log of 2/15 divided by negative 0.01. And I hope you're going to grab your calculator to calculate this for me. I'm hoping you're coming up with approximately 201.5 minutes. That's how long it'll take the 15 kilograms of salt that are in this tank to reduce down to 2 kilograms. Okay, I've done 2 examples in this video. Both of them are looking at a problem where the inflow and the outflow rates are the same. I'd like to do another example for you, but I'm going to do it in another video. And so in my next video, I'll cover an example where the inflow and the outflow rates are not the same. I hope this is helpful, and I'll see you in the next video.